All right, so in this lesson, we're going to talk about how to solve exponential equations and inequalities. All right, so an exponential equation is when you have an equation where the variable is now in the exponent. All right, so um, let's talk about this property of equality, right? If you have b to the x equals b to the y, right? Then you can set x equal to y. So let's really take a look at the premise here. You have a base to the power of an exponent. You have the same identical base to the power of a different exponent. That's when you can set the exponents equal to each other. Okay, click once, either turn it on or turn it, open it, or okay, and then that's it. Okay, thank you. Okay, so these have to be identical, and if they're identical, then you can set the exponents equal to each other. All right, so take a look here. I have 3 to the power of x plus 3, 9 to the power of 4. Okay, so this is the elemental base, so I leave it. Okay, this 9, I can write it as a base of 3, right? This is 3 squared to the power of 4. So really it looks like this. Okay? And so what do we have now? X plus 3 is equal to 8. Okay, now we're past chapter 6. We're past algebra 1 where you first learned about exponents. We reviewed about exponents in chapter 6. In algebra 2, we're no longer at this stage. After having done chapter 6, we're no longer going to get confused about when do I multiply exponents and when do I add exponents. That's the thing in the past. All right? If you have something to the power of something else, multiply the exponent so that becomes an 8. Okay, so now x is equal to 5, and that's it. Now, what is the domain for all exponential functions? All real numbers. Because it's all real numbers, there are no restrictions on the domain. I don't have to plug it back in to check. Like you can to double check to see if you got the right answer, but there are not going to be any extraneous solutions. Okay, so here too, I have 2 to the 5x equal to 2 squared, right? That's how I write the 4. And then this exponent multiplies. So now I set these equal to each other. So 5x is equal to 4x minus 2. X is equal to negative 2. All right? Okay, here. All right, I have a 1 over 5 and I have a 25. So it's probably best to make both of them 5. Okay, so 1 over 5 is 5 to the minus 1, right? To the power of x minus 5. This is 5 to the power of 2 to the power of 3x minus 2. Now I'm going to set these exponents equal to each other. So I'm going to get negative 1 times x minus 5, negative x plus 5, equal to 6x minus 4. So 9 is equal to how much? 7x. That means x is 9 over 7. And that's okay. So we get a fraction. It's fine. All right. Questions?
So you can just set the negative 1.
Correct. Okay. So here, I have root 3. Root 3 is the same as 3 to the power of 1/2. 3 to the power of negative 3x. 1/2 is equal to negative 3x. Divide by 3. I'm sorry, negative 3. So x is negative 1 over 6. All right? Okay, now, inequalities work in the same exact way. If I have b to the x greater than b to the y, if they're the same bases, then the inequality just transfers to the exponents. X is greater than y. All right? Okay, so let's go ahead and solve this. So I have 2 to the power of x plus 2. greater than, how am I going to write this? 2 to the negative 5. Okay? So, okay. Everybody okay with that?
Wait, how did you get there? Sorry.
Okay. 1 over 32 is 1 over 2 to the 5. Right? So this is 1 over 2 to the 5. But this is just 2, and that's 1 over 2. So 2 to the x plus 2 is greater than 2 to the negative 5. Okay, so x plus 2 is greater than negative 5. X is greater than negative 7. Okay, here. I have 5 to the power of 3 minus 2x, less than or equal to. So let's think about this for a minute. I have a 5, and then I have a 1 over 625. The 5 is a numerator. This is in the denominator. To make them both, right, the same level, you have to have a negative exponent. So let's just think of 625 first. 625 is 5 to the power of 4. It's 5 to the power of 4, because 5 cubed is 125, 5 to the 4 is 625. So this is 5 to the power of 4. Now, to go between a whole number and a fraction, it's a negative exponent. So that will be 5 to the power of negative 4. So 3 minus 2x is less than negative 4. Negative 2x is less than negative 7. X is greater than 7 over 2, equal to. These are all equal to. Don't forget the switching, okay? The switching of the sign. Okay. All right, any questions? Okay, let's move on. Okay, so how to write an exponential function? To write an exponential function, you have to substitute any information you're given into this general form. All right? Remember what we talked about yesterday. Yesterday we said that A, the initial amount, was the y-intercept. Do you remember that in yesterday's problems? The initial amount is the y-intercept, A. All right? Okay. So substitute A into the y-intercept and x comma y, right? Okay. Solve for B and substitute A and B back into the equation, leave x and y as variables. Okay, this just got very complicated, so we're just going to do one and then we'll go over the steps as we're doing it. Okay, so take a look at this. Write an exponential function for the graph that passes through the given points. Okay, so I have 0, 6.4, right? When x is 0, right, this is the initial amount, right? Because think of x as your time. So when t is 0, this is 6.4. So another way to think about it is this is the y-intercept. If this is the y-intercept, that means this is the initial amount. Once you've locked in your initial amount, the other coordinate is x comma y. So now the form that I'm going to substitute into is y equals a times b to the x. So y is 100 equals a 6.4 times b to the power of x, which is 3. Do you see that? This is the important part. After this, you know what to do. But x and y, 3 and 100, a is the 6.4, the y-intercept, the initial amount. So now what we're going to do is we're going to divide by 6.4. So, and I'm going to go ahead and take out your calculators, please, so you can do this with me, because I'm going to do this. So let's do doc B. Okay, let's just do this right now, and then we'll talk about quizzes, okay? Okay, so let's do 100 over 6.4. I get 15.625. Okay, so I'm going to write that here. Okay, now to solve for b, what am I going to do? Cube root. Okay, I understand right now we got 15.625. That's a rational number, but most of the time you'll get something that's irrational that never ends, right? So this is very, very important. You are not going to round in the calculator. So here you're going to do the cube root of the previous answer. So you're going to do control answer. Now, I get it. This is small enough that you could have retyped. But what if it was some non-ending rational number? That you couldn't have done. So here, that gives you 2.5. So B is 2.5. Yes.
It's really cute. We did something just like this on the homework.
Yeah.
Yeah, for number 7.
Similar. Yeah.
Just like
Yeah. Okay. So now we're back here. Substitute A and B into the main equation. Right? Substitute A and B. Leave X and Y. So Y is equal to A times B to the power of X. So that is your final equation. Okay? Okay.
Wait, you wouldn't multiply though because you have to
No.
know that.
Okay. So so let's go to the next one. Kristen starts Kristen starts an experiment with 7,500 bacteria cells. After 4 hours, there are 23,000 cells. Okay, so you have to identify two things: an initial amount and another point in time. Okay, this is the initial amount. That's what. How come this happens only in this class? Okay, this is the initial amount. That's what we start with. And then you have to have another snapshot of another point in time. And that is this one here. 4 hours, there are 23,000 cells. So that's 4 comma 23,000. Okay, and now with exponential functions, right? When the numbers get so large so quickly, when you put coordinate forms, you're going to have multiple commas, right? So it's going to be up to you to like keep those commas in check, right?
Oh,
Okay.
we have to do commas now?
Okay. Right. So let's write an exponential function. So same situation, right? So the 23,000 is the initial, is the y, equal to the initial amount times b to the power of x, which is 4. Okay, now, whenever you have something like this, you can always cancel an equal number of zeros from either sides of the equation. So now we have 230 over 75 is equal to b to the 4. I take a 4th root. Do you see how I didn't even waste time to plug that into my calculator, right? So now I take the 4th root and I have the 4th root. So control here, 4th root of 230 over 75. 4th root. Okay. Once you press enter, before you mechanically type in your answer, double check to see that this input here is the same as what you meant to input. There have not been any typos and so on. Like, for example, right now I had just missed the 4 if I didn't go back and check. All right, so B is 1.323. And if I haven't specified, 3 decimal places is always a good number. So we're going to have y equals the initial amount, 1.323 to the power of x. Okay, how many bacteria cells can be expected after 12 hours? Well, now it's going to be y of 12. I do want this notation in my honors classes, right? Y of 12 is equal to 7,500, 1.323 to the power of 12. All right. So, okay, hang on. Okay, we're going to plug it into the calculator now. 1.323 is the rounded value, correct? We are not going to use the rounded value. So here's what we're going to do. 7,500 times. We're going to use this answer. So we're going to do control answer to the power of 12. And so now we get 21, how much? 216,302. Well, hang on. Okay. How many, okay, so look at the question. It says how many bacteria cells, right? How many individual bacteria cells? You're going to round correctly mathematically. So this is 216,302 cells. All right, question?
When you press Control T on the graph, how do I make it so I can see decimals?
I actually don't know. I have to think about it.
I couldn't find a way to stretch it because it only shows the whole number.
I don't know. I have to think about it. It's somewhere in the settings. But it's actually faster to do it this way sometimes. Okay, so now let's talk about compound interest. Compound interest is another place where we use exponential functions. Compound interest is when you put money in a bank account, like a saving account, or a savings account. And then let's say you put $1,000 in, okay? And the first year they give you 10% interest, right? So now you have $1,100. And then the second year, they give you 10% interest on the new amount, on the $1,100, right? And then the third year, they give you the compound on the new amount. So, it keeps adding to itself. That's compound interest. So here's the formula. This is the formula right here. Yes, you have to memorize this. So it's A equals P, 1 plus R over N to the power of NT. Okay. So P is what we call the principal, but not like Miss Howard, the principal. This is the money that you first deposited into the bank. Rate is R. N, this is important. N is the number of times in a year the bank is paying you money. And there are different accounts and different banks. So one account, the bank might say, okay, we're going to pay you interest 3 times a year. Another one says, okay, we're going to pay you interest 12 times a year, every month. Another one says we're going to pay you interest annually, once a year. So that changes. So some sample values of N, right, are over here. If it says yearly or annually, N equals 1, monthly, and so on. Quarterly, there are 4 quarters in the year, so 4 times. And then bi-monthly, that's every 2 months, so 6. Okay, let's do a couple. A sum of $8,000 is deposited into an account that pays 5% interest. Find the balance of the account 15 years after if the interest is compounded quarterly. Okay, lots of information here. First, 8,000, that's your initial amount, P. 5% interest, so R is 0.05. Find the balance of the account after 15 years. This is your T. If the interest is compounded quarterly, that means N equals 4. Okay, so the formula is A equals P, 1 plus R over N to the power of NT. So A equals 8,000, 1 plus 0.05 over 4 to the power of 4 times 15. Okay, that number N shows up twice. So you plug it in one shot. 1 plus 0.05 over 4 to the power of 4 times 15. Okay. Now, you're not going to be told what to round to. But this is money. It's dollars and cents. You got to go to the second decimal place, right? So this is going to be 16,000. $857.45. You have to be able to round properly, guys, please. It can't be 44 cents. It can't be 46 cents. Can you imagine if banks were off by like a penny for every one of their customers? Can you imagine, like, it's millions of dollars over a couple of years, right? Didn't Wells Fargo get into trouble for doing that a couple of years ago? They were like embezzling
Is there
money
a-
like that. There was
is
like
there a
little
way to
errors.
have it so like after like 4 years you put another 5,000 in there, and after like 5 years you just added a certain, like every year, let's say you put 500 more in there.
So then that's like another formula because you have to add to the formula. This is
My calculator just gave me 0.5. So how do I fix that?
So go to menu. I'm sorry, not menu. In the scratch pad, so press dock. Go to settings, number 7. Document settings. This first one, display digit, has to say just float, not float 6, just float. When you say float, it's for the whole thing.
Wait, what do you press?
Okay, menu, not menu, dock, 7, document settings, and it's right there. All right, any other questions? Okay. All right. A savings account offers 0.8% interest compounded bi-monthly, so n equals 6. If 150 is deposited in this account, what will be the balance after 20 years? Okay, so A is equal to 150, that's the initial amount, 1 plus, okay, R, what's R going to be? 0.008, be careful, over 6 to the power of 6 times 20. I need to see this written out, all right? On the test, quiz, whatever, I need to see this written out. So 150 times 1 plus 0.008 over 6 to the power of 120. Okay, so go ahead and plug that in. Is that what you guys got? 176.01. Okay, so let's see here. Right? So this one, right, it rounds to 1. Okay, so in 1995, the population of Planet Algebra was about 6.248 million. By 1995, it had decreased to 4.97 million. Write an exponential function that could be used to model the planet's population, y, in millions from 1965 to 1995. Okay, so lots and lots of information here. Okay, first of all, let's see here. The initial amount in 1965 is this. So now take a look here. It says X is the number of years since 1965. So in 1965, X is 0. So that's the point 0, 6.248. That's my y-intercept. That's my initial value. By 1995, it had decreased to 4.987. So in 1995, that's 30 years after. Now the new amount is 4.987. When it says the population Y is in millions, that means when it says 6.248 million, I can just write 6.248, but all my values I know are going to be million. Okay? So let's go ahead and write this. So the initial amount, the final amount, 4.987, is equal to 6.248 times B to the power of 30. Okay? So this is the initial amount, and then 30 is X, 4.987 is Y. All right. So we divide. Okay, so now let's see what we're going to get. 4.987 divided by 6.248. Okay, you see how I got this crazy irrational number. Okay, I'm going to put some placeholders here. So 0.7982, let's say. 0.7982 equal to b to the power of 30. Let's take the 30th root and the 30th root. It's okay, the calculator does it for us, right? So here, I'm going to do 30th root tab of what? Answer. Enter. Okay, so B is 0.9925. Okay. Okay, so take a look at what it says here. It says to round B to the nearest thousandth, right? Which is 3 decimal places. So in my equation here, it's going to be y equals 6.248 times 0.993 to the power of x. That's my equation. Suppose the population continue. Oh, so is this an exponential growth or decay? Decay. And do you see how, because it's decay, right, B turned out to be less than 1, somewhere between 0 and 1. Do you see that? Like, that has to happen every single time. Okay? So now, suppose the population continues to decrease. Estimate the population in 2005. In 2005, starting from the initial 1965, now T is how much? 40. So we're going to do y of 40, which is 6.248 times 0.993 to the power of 40. And again, we're not going to round. So it's going to be 6.248 times the answer that we just got to the power of 40. If you round, it'll be a little bit off. 4. Is that right? 4.62. Okay. So this is what? Wait, what was it? 4.6259. Okay, so 4.626. Okay.
It went up.
No, it didn't go up. It went down. Okay. Now, so how much? So what do I write for the answer then? 4.626 million. Okay, now I also did this without rounding. With rounding. Okay, I did it with rounding, and I got, don't write this down, but I got 4.717 million. Okay, so this is 4,626,000. So compare 626,000 to 717,000. That is a lot of people that you are getting wrong, right? And if you're talking about, like, you know, figuring in like budget for aid and this and that, like, imagine you're now like discounting about, like, you know, 50,000 people, which is not cool, right? So do you see, even though it's just 1 decimal point, but in the context of millions of people, it's 50,000 people, or no, more. It's like, it's about 100,000 people that you're just discounting. So do you see the ramifications? It's not just like, you know, a little thing. Okay, estimate when the population will reach 4 million using your graphing calculator. Oh, I have a typo there. Okay, so let's graph this. There shouldn't be a question mark there. Okay, so let's graph this. So I have, give me a second. I have 6.2. I was just thinking about that. Okay. Oh my God. Why isn't this? This went on very completely. Okay. I'm having. Let's do 0.993 for the time being. And then tomorrow I'll show you guys how to store a variable so you don't have to do that, okay? So to the power of x, okay? So it says estimate when it'll reach about 4 million. All right, so let's bring this, let's fix the windows a little bit. So Windows settings, I want to go X max from 0 to about what? I want to go 100 years. All right, and let's go from 0 to 10 here. I just want to make a pretty graph. Okay, that's a prettier graph. So what do we want? 4 million. Okay, again, I want to show you guys the intersect feature. So in your calculator, press tab and put 4. Okay, now that's the 4 million mark. All right, this is important as you move up to pre-calc and calc. Tab in F2, put in 4. That's 4 million. Now we're going to find the intersection. Okay? So that's about...
How did you find where they...
Okay, so menu, analyze graph, intersection. Remember, this is what we were doing for the chapter 3, like the graphing.
Yeah, I do that, but that point, yeah. How do I change my window settings?
Okay, hang on. I have only a couple of minutes left. So this is 63.5. Right? So it's about 63.5 years. Now, it says, yeah, estimate when. So you want to give the year, right? So it's about 2028. It's like in the middle of 2028. Yeah? Okay.
Did you go from
So we're going to take that last answer. Oh no, wait, that wasn't it. It was this one. This answer, I'm going to store it in the calculator so that I can use it. So press the top, this up button, go up to that value, press enter, so now you bring it into the edit field. Now, this number, the 0.999. Okay, so now, look here. In this row, you have control, you have shift, you have the VAR, that's the variable button. Right above it is STO, which means store. Okay, so here's what you want to do. You want to do control and that variable button, basically store. And I want to store this as A. So type in A, right? Press enter. And now that one is stored. So now look, so if I press A now, enter, it gives you that value. So let's go to the graph here, right? Let's edit this. Take out the 0.993. Let's put in A. Do you see how it's bold? Okay, so now it's like 59.3. Like, do you see how like it's shifted it a little bit? You see that? Isn't that cool? So cool. So you can save one thing as A, another thing as B, another thing as C, but you know, like
should we change
keep
our